Welcome to this channel. In the last episode, we have trained our first machine learning model for a simple linear regression problem on our toy dataset. In this episode, we will prepare the foundational steps for the next episode, where we will utilize stochastic gradient descent in order to make our training process more efficient when dealing with more complex data. After following along in this episode, you will be able to implement the Dataset and Dataloader classes, which will be able to do the following things. The Dataset class will hold our dataset and will be able to use the length method on our dataset instance in order to retrieve the number of instances, and we will be able to use an index axis to retrieve elements out of X-train and Y-train. The Dataloader class will be able to function as an iterator, making our Dataloader instances iterable and returning batches of data. So as you can see, this is the code which we will write in this episode, and I hope you have a lot of fun. As you can see, when we execute it, we get batches of data. So if you want to know how to implement it yourself, follow along in this episode. So let's start and have fun following along. First of all, we need some dataset in order to test our Dataset and Dataloader classes. So we will implement a class that helps us to generate some toy dataset. In this case, we are just generalizing our linear toy function from the last episode. So let's code up how we would like to use our helper class that generates some toy data for us. So we would like to have a class SyntheticLinearDataset that would allow us to pass the following arguments: y-slope, y-intercept, and the number of instances we want to have. And we should also be able to use the method generate in order to get our toy dataset for x and y. And we also print the shape of x and y in order to see if it matches the number of instances. So let's implement our little helper class. So this is nothing special. We have just implemented a very simple initializer for our class. Next, we will implement the generate method, the function that we use in order to generate our toy dataset. And it's the one essentially from the last episode, just that we have generalized it a little bit in terms of that we can choose the y-slope and the y-intercept. So let's code it up. So let's execute our script in order to see if it works. And as we can see, it works. At least it does not raise any errors. Next, we use X in order to create X-train, as we also did in the last episode. For this episode, it does not actually matter whether we use X or X-train. Let's code up the data loader and how we would like to use it. So our dataset class should accept the following arguments: X-train and Y-train, because this is essentially our data that we have. So let's create this dataset. So as we can see, the initializer is also very simple. We are just checking if the length of X train and Y train is the same. Actually, yeah. And if this isn't the case, we just throw a value error. And we also save the number of instances. Next, we need to implement two dunder methods on our dataset, which are just for convenience. The dunder method for the length method and the getItem such that we can access any element from our dataset with an index. So let's do the length first. So this is very simple. We are just returning the number of instances. Next, the getItem dunder method. So that's it. What we are just doing with a getItem dunder method. So we have as the argument the index, and what we do is we just return self-X train evaluated at that index, and the same for self-Y train. So we're returning a tuple. That's it. Next, we are gonna implement the DataLoader class, which is a little bit more interesting than the dataset class, because it does a lot more than just holding some dataset. So let's code up the DataLoader and how we would like to use it. So this is how we would like to use the DataLoader class. And we would like to pass the following arguments. We would like to pass the dataset, of course, the batch size, and if we want to shuffle our dataset at each iteration. Because the DataLoader we are going to implement is iterable. And so when we iterate over our DataLoader, we want to get back batches of data. And the shuffle parameter determines if we are shuffling the dataset from which the batches are drawn on each iteration. So let's implement this class, and let's start with the initializer again. This initializer is a little bit more interesting than in the dataset case because we are introducing two important instance variables, the index and the terminating state. The index will help us to determine at which iteration count we are when we are iterating over our DataLoader instance. And the terminating state will indicate us whether we should stop iterating or not. And what is also interesting is that we are copying the dataset. So the X train and Y train, we are copying it. Why do we do that? Because we will see in a minute when we are shuffling our dataset, we don't want to shuffle the actual dataset. The actual dataset should stay immutable. So we are copying it. In order to implement the DataLoader as an iterator, we will have to implement the following two dunder methods, the iter and the next method. So when we loop over a DataLoader's instance, iter is called implicitly and will return an iterator. In this case, DataLoader is the iterator, so it will return only self. We will see that in a second. And the next dunder method is used on the iterator in order to iterate over it. Let's start with the iter dunder method. As you can see, we just return self, since DataLoader is our iterator. Next is more interesting, so let's continue with it. In order to implement an iterator, it's actually very helpful to use a try-catch block in order to catch the index error. This error will be raised when we will stop iterating. And in the catch block, we raise the stop iteration in order to signal that we are finished iterating over our iterable. We will also use the catch block in order to reset our instance variables such that when we iterate a second time over our data loader instance, we will get the same result. And of course, we increment our index in order to track the iteration count. So far so good. Let's code the interesting part. What comes into the try block? So let's break it down step for step and let's think a second about it. So if shuffle is set to true, then we will simply shuffle our dataset. So let's start implementing this. We are gonna use NP-random permutation in order to obtain this set of indexes. So that's it for the shuffling. Quite easy so far. Now we need to select the boundary indexes in order to retrieve our batch. So the beginning of the batch will be self-index times self-batch size, right? Because when self-index is equal to 0, and that's where we start, then we will start from 0 onwards, because 0 times the batch size is 0. That's exactly what we want. And when the index is equal to 1, then our next batch will start from the batch size onwards, and so on. The end of the batch will be therefore self-index plus 1, and the whole expression times the batch size. So let's implement this and talk about one important edge case. So we have to be careful with this because suppose we have 1000 instances in our dataset and our batch size is 128. Then we can only have 8 batches of data, but the last batch will not contain 128 values, but only 104 values, since 7 times 128 plus 104 is equal to 1000. So what we have to be sure of is that when we reach the last batch, that we only go up to the last value and not more. So here's the trick on how to solve this. We just use the min function. So if we go beyond 1000 instances, the min function will go back to the last instance. Now if self-terminating, this is what we have to code up now, is set to true, we should raise the index error in order to stop the iteration. So let's deal with the state management of the terminating state and when we should set the terminating state to true. As I said, if terminating state is reached, so if self-terminating is true, we should raise the index error, which will signal the end of the iteration. And when should we set the terminating state to true? This is the case when the second index of our boundary is equal to the length of a dataset. If that is the case, we know we've reached the end of the dataset. And then we set self-terminating to true. And the order of those two if statements are important, since when we would get our last batch and would stop the iteration, then the last batch would never be returned. In this way, we make sure that the last batch is returned before the iteration stops. Finally, we just need to return the batches. This can be done in the following way. So drawing the batches is quite easy, right? We just use our boundaries that we calculated in order to draw the batches, and then we return it in the end. So the implementation of next is not done yet. What we have to do now is to reset our instance variable such that when we iterate a second time over it, that it still works. So let's do it quite quickly. And that's it. So what we reset is the X train, Y train, the index is again set to 0, and the terminating state is again set to false. That's all we have to reset. And now you see why we have those instance variables in the first place, because we could also put them here into the try block, but then we would have a problem that at each iteration we would copy the whole data set. This is not what we want at all, because that would incur huge performance penalties. And note, this is not a very highly optimized data loader in dataset class, but it just serves for educational purposes in order to understand what is happening in such classes. For instance, PyTorch uses the DataLoader class, and it's always helpful before using such classes to think a second about it, how it actually works, or could work in principle. So let's conduct a small experiment in order to see whether our data loader is indeed working. So we defined our data loader here already. And now what we're gonna do is we iterate over our data loader and see if the iteration is working. And let's also print out the length of the X train batch and Y train batch in order to see if we did everything correct. And what we also want to do is add a little counter in order to see if the number of iterations is equal to the number of the batches we wanted. So the counter is useful in order to see how often we iterated over our data loader and to see if it matches. So let's execute the script and see if it works. Oh. Yeah. And yes, as we can see, indeed it's working. The number of iterations is 1000, and this is what we would expect since our batch size is equal to 1. And if our batch size is equal to 1, we should get, in each iteration, we should get one data point for X train and for Y train. And this is indeed what we get, as we can see here from the output. And we iterated 1000 times, because this is the number of instances. Now, let's use another batch size, 128. And as we said, with 1000 instances, we should iterate 8 times. And indeed, this is the case. 1, 2, 3, 4, 5, 6, 7 times 128 batches, and 101 batch with only 104 data points in it. And this is also exactly what we wanted. And now let's set the shuffle argument to true, and let's see if the output is still the same. Oh, yeah, as we can see, there's a small error, but we can correct it real quick. We just have to use suf on those guys. And now execute it again. And indeed, our shuffling is also working just fine. So let's do another experiment, a small test. Let's do it 2 times in a row in order to see if the result is really the same, because this is really important for us that when we execute it multiple times, we should get the same result. And as we can see, the first time we get now 8 iterations with the correct batch size, and a second time also as we would expect. So yeah, to sum up, our reset is working, our shuffling is also supposed to work, we can define a batch size, and we can iterate over a data loader in order to get the batches. So thank you for watching this episode. If you want to see more of this series, subscribe to this channel, and see you in the next episode where we will implement stochastic gradient descent. See you then.